All right, this is the Unit 6 Part 1 notes over moles, percent composition, and empirical and molecular formulas. Since we're just doing Part 1, we're just going to be talking about moles. All right, so just a few reminders from the last unit. I wanted to remind you about diatomic elements. We talked about diatomic elements in Unit 5. And remember, they are the elements that always show up in pairs of 2. And so they are actually their own sort of compounds in themselves. And these are the elements that are stable only in pairs. And or they'll always be combined with another element in a compound. So the way that I always reminded you to do diatomics was to say your H Broncliffs. And the H Broncliffs would include hydrogen, bromine, oxygen, nitrogen, chlorine, iodine, and fluorine. Notice there's 2 of every one of these since they're by themselves, and that's why they're diatomic. So let's talk specifically about Part 1. All right, the mole. This is a really important concept that will be carried over all throughout the rest of the year. But the mole is really just an amount of a substance, and the amount of that substance is 6.02 times 10 to the 23rd particles. This number of 6.02 times 10 to the 23rd is also called Avogadro's number, so it's given a specific name, but those particles are what represents a mole. Now, what are representative particles? And since a mole is a certain number of particles, what do those representative particles mean? A representative particle is the form in which a substance exists. For example, atoms, molecules, or formula units. Atoms exist when you have elements. So, oops, I didn't want to do that. Let's see if I can get that to come back up. There we go. So atoms are when you have elements. Their representative particles are of elements is atoms. When you have the representative particles of a molecular compound, you have molecules. And when you have the representative elements of an ionic compound, you have the formula units. So all of these mean the same thing, but we'll use them at different times depending on what type of compound or element we're talking about. So a dozen representative particles equals 12. So what we would say is really that a mole, I guess I need to erase my stuff up here. A mole of representative particles is 6.02 times 10 to the 23rd representative particles. So really, if I said a mole would be equal to 6.02 times 10 to the 23rd atoms. And a mole is equal to 6.02 times 10 to the 23rd molecules. And a mole is equal to 6.02 times 10 to the 23rd formula units. So this representative particles right here can be replaced with any of these words, depending on what we're talking about. Okay? So a mole is really just a convenient way to count large numbers of atoms, molecules, formula units, or even just ions. We're going to use dimensional analysis, which we did way back at the beginning of the year, to solve these types of problems. So we're really just going to set it up, cancel out units, and convert from one form to the other. So really we just created a whole bunch of conversion factors. So, conversion factors. 1 mole is 6.02 times 10 to the 23rd representative particles. If that's the case, then we can set up our little conversion cards as a way to think about it. And that would be that we could have 1 mole on top with 6.02 times 10 to the 23rd representative particles on the bottom. Or we could have 6.02 times 10 to the 23rd representative particles on top and 1 mole on the bottom. We would use one of these conversion factor cards. Really, we could look at them like that, depending on how we want to convert. So here, let's do some examples. How many moles are 1.2 times 10 to the 25th atoms of phosphorus? Phosphorus is an element. Its representative particles would be atoms. So we start with the number we're always given. So we are given this value of atoms. We are wanting to find moles. So when we start our dimensional analysis, we start with what we're given. 1.2 times 10 to the 25th atoms. We set up our little T-bars. Somebody the other day called them train tracks, so I guess that's a good way to look at them too. But if atoms is on top, then our next conversion needs atoms on the bottom. And we're trying to go to moles. Well, we know that there's 6.02 times 10 to the 23rd atoms for every 1 mole. So we can put that number there and put that number there. Okay? That allows us to cancel out our atoms, and we'll end up with just moles. If you remember with dimensional analysis, we multiply everything across the top and divide by everything in the bottom. When you're doing your math on this, remember that we have our times 10 value on our calculator. We'll just use the EE button. It's next to the letter A if you have the Inspires. But you really want to try to stay away from your times 10 to the caret button if you can. Also, the other thing we need to think about is not only are we using dimensional analysis, but we need to pay attention to significant digits still. So when we start right here, we have 1, 2, 3 significant digits. Since we have 3 significant digits to begin with in my original number, that's all I can have in my answer. So when I do this in my calculator, I'm going to get 19.9 moles. That's 3 significant digits, so that is my answer. All right. Our next one, how many molecules are in 0.400 moles of N2O5? So we start off with these moles and we're going to molecules, which are representative particles. So thinking back to our little conversion factor cards, we're going to set this up and we have a mole that we're starting with. Also, we have 1, 2, 3 significant digits, so that'll be important for later on. So we start with our dimensional analysis, and if moles is on top, then moles needs to be on the bottom. And we're going to molecules, which is representative particles. We know that there's 6.02 times 10 to the 23rd representative particles for every 1 mole. Since those are both on the top, we'll go ahead and multiply. When we get this in our calculator, we will go ahead and round to 2.41 times 10 to the 23rd molecules. Okay? So how many moles are contained in 1.2 times 10 to the 24th molecules of CO2? So we're starting off with molecules and we're wanting to go to moles. So again, we have 1.2 times 10 to the 24th molecules. We draw our little T. Molecules is on top, so molecules needs to be on the bottom. We want to go to moles, so we know that there's 6.02 times 10 to the 23rd molecules for every 1 mole. This will allow us to cancel out our molecules. We'll just be ending up with moles, and we'll divide since it's on top and bottom. And in your calculator, you end up with this number, but we're only allowed to have 1, 2, 3 significant digits. So we would round this to, we would count 1, 2, 3. This is a 3, so that's not going to round up. So it would be 1.99 moles. All right. So let's talk about some vocabulary real quick. We have gram atomic mass, and this is the mass of an element expressed in grams. Okay, pretty easy enough. Those are what the words say. What we're going to do is we're going to use the periodic table to figure out these values, and we're going to take masses to the nearest 0.1 or the 10th gram. So when you look at the periodic table, there's like a whole bunch of numbers after the decimal. We're always going to round it so that there's just one number after the decimal. So we'll always look at the second number after the decimal accordingly to round. So let's do some examples. When you look up carbon on the periodic table, okay, I want to know what its gram atomic mass is going to be. So I have some options here. Remember I said I'm always going to round it to one number after the decimal. Well, on the periodic table, it actually says this. If I rounded it to the 100th, it would be this. But I want to round it to the 10th, so that'll make it this one. So C would be the correct answer for this. All right, let's look up nitrogen now. All right, and nitrogen, we have some options for it as well. So when we look at the periodic table, this is the value that we're given on the periodic table. This is rounded to the hundredth. This is rounded to the tenth. So we would make B our actual answer. Then for sodium, sodium on the periodic table is this. Rounded to the 10th is both my A and my B. But what we need to do is we need to look at this digit right here. That's a 9, so that's going to cause this 9 to round up. When that rounds up, that's going to cause this to round up. So when we round that up, this is actually going to be the correct answer. So we'll use 23.0 for sodium. Okay. Then we're going to look up chromium. Chromium on your periodic table is this one. So if you remember, I said look at the hundredth position, or the second number after the decimal. That's a 9, so that's going to cause the other 9 next to it to round up, which is going to make A our actual value of 59.0 grams. All right, then let's look up boron. Okay, boron is 10.812 on the periodic table. So rounded to the hundredth, it would be this. But we don't want to round it to the hundredth. We want to round it to the 10th. So the 1 doesn't cause the 8 to round up. So our answer would be 10.8. Okay, you do need to know how to round all of these numbers properly so that you'll be able to do calculations later on accordingly. All right, so now let's talk about the gram molecular mass, okay? So we just talked about the gram atomic mass, and that came off the periodic table. Well, the gram molecular mass is when we have a molecular compound, and it's going to be the mass that we use for 1 mole of it. So what we'll do is we'll take all of the gram atomic masses of each of the elements, and we will take the sum of those. So we're going to add them all together. All right, so an example would be like H2O. How many, we have 2 elements there. We have hydrogen and we have oxygen. And if we look at the subscripts, we have 2 hydrogen atoms and we have 1 oxygen atom. Then we're going to look up the GAMs off of the periodic table, or the gram atomic masses. Hydrogen is going to be 1.0 grams, and oxygen is going to get rounded to 16.0 grams. So now we're going to do that multiplication. 2 times 1 equals 2, and 1 times 16 equals 16. And then we're going to find the sum of those two. So the sum of those two would be 18.0 grams, and that would be grams per mole. So that would be the gram molecular mass. Okay, we could do another one. We have 3 elements here. We have carbon, we have hydrogen, we have oxygen. We have 1 carbon. We have 3 plus another hydrogen, so that would be 4 hydrogens, and we have 1 oxygen. Then we're going to look up the atomic masses off the periodic table, and carbon is going to be 12 when it's rounded, hydrogen is 1.0 when it's rounded, and oxygen is 16.0 when it's rounded. Then we're going to do our multiplications. 1 times 12 is 12, 4 times 1 is 4, and then 16 times 1 is 16. Then we're going to take the sum of those. 12 plus 4 plus 16 gives me 32.0 grams per mole. Now, these molecular masses are always going to have 1 decimal after the 1 number after the decimal, and that's because if you remember your significant digit rules for adding was that we look at the smallest amount in our numbers that we're adding, and there's always 1 number after the decimal in all of these, so our answer should also have 1 number after the decimal in it. Okay? All right, so then we have the gram formula mass, which is the GFM. And the only difference in this one is that this is the mass of a mole for an ionic compound instead of a molecular compound. But it's really still just the sum of each of the elements' gram atomic masses of the compound. So the GMM and the GFM are all the same. They're really just sums. All right, so if I want to know what the gram formula mass, or the GFM, for magnesium phosphate is, well, first of all, I have to write the formula, which we did in our last units. So this is one of those things of, let me review you from our last unit. So we have magnesium, and we look it up on our periodic table, and magnesium symbol is Mg. and its charge, since it's in the second column, is a positive 2. Now, phosphate is a polyatomic ion, so it's on the back of your periodic table. And it is the formula PO4, and it has the charge of a negative 3. When we did our our ionic compounds, we took these charges and we crisscrossed them down. So when we do that, we would end up with the compound Mg3, open parentheses, PO42. So that's, remember, a review of those compounds. You are expected to still know that information because a lot of the activities that we do in class, as well as the homework, will require you to go back over that material. So make sure that you really remember our last unit. Okay? So now we're trying to find the GFM, so we need to identify our elements. We have magnesium, we have phosphorus, and we have oxygen. Well, how many magnesiums do we have? We have 3. Now for phosphorus, we only have 1 for the subscript, but that's inside of a parentheses where there's a 2 on the outside. So what you have to do is you have to distribute that 2 to both of these numbers. So there are 2 phosphorus, and then 2 times 4 is going to give me 8 oxygens. All right? So you do the same thing like you would do in math. If you have a parentheses, you distribute that subscript outside the parentheses to all the subscripts inside the parentheses. So now we have magnesium. We're going to look up our atomic masses off our periodic table. And magnesium would round to 24.3 grams. Phosphorus would round to 31.0 grams. And oxygen would round to 16 grams. Then we would do our multiplication. 3 times 24.3 would give us 72.9 grams. 2 times 31 would give us 62.0 grams. And 8 times 16 would give us 128.0 grams. We would then take the sum of all of those, add them all up. They all have 1 digit after the decimal. So our answer has to have 1 number after the decimal, which would give us 262.9 grams per mole. So it's real important that you remember that the gram formula mass, the gram molecular mass, and the gram atomic mass are all grams per mole. All right? So here's another one, aluminum hydroxide. Well, aluminum on the periodic table is Al. It's in column 3A, so it's a +3 charge because it loses 3 electrons. Then hydroxide's a polyatomic ion of OH with a -1. So again, when we crisscross those charges down, we get Al1, OH in parentheses, 3. Okay? So then we have Al, our 3 elements are Al, O, and H. We have 1 Al. We distribute that 3 to everything inside the parentheses. So we have 3 O's and 3 H's. We then multiply, and we look up the atomic masses off the periodic table. So we say that aluminum is rounded to 27.0. Oxygen is 16.0, and hydrogen is 1.0. Then we multiply, and we get 27.0 grams for aluminum, we get 48.0 grams for oxygen, and we get 3 grams for hydrogen. Then we add the 3 of them together and take the sum. Because there's 1 number after the decimal on each of these numbers, our answer also has to have 1 number after the decimal. So it would be 78.0 grams per mole. This is a really important concept as we're going through that you're going to have to be able to use. So you really need to understand how to calculate the gram formula masses. All right, so the gram formula masses is really just a generic term for all the terms we just discussed. Gram atomic mass, gram molecular mass, gram formula mass, all of them can be lumped into one big saying and say GFM. Okay, I will also say another name for them, which this is part of your homework, so we can use them for any of the compounds. But another name for it is molecular mass. So if I ask you to find the molecular mass, I'm really just asking you to find the mass for a mole or the GFM. Or you could call it the molecular weight. Okay, all of these terms mean the same thing. So I could call it the gram molecular mass. I could call it the gram formula mass. I could call it the gram atomic mass. I could call it the molar mass. I could call it the molecular weight. All of them are the same thing. Okay, we typically use molar mass and GFM the most. I will say that. So really, this is just another conversion factor. So originally we had the 1 over 6.02 times 10 to the 23rd representative particles. Well, now we also have 1 mole over the GFM, or we have the GFM over 1 mole. So this again is just a way to convert using our dimensional analysis. Okay? So if I wanted to find the mass in grams of 3.32 moles of potassium, which is K, I start off with my moles. I'm trying to find my mass in grams. So I'm going to do some dimensional analysis, and I start with what I'm given. If moles is on top, then my next conversion has to have moles on the bottom. Well, I know that I can look up the gram value for potassium on the periodic table. So when I look that up, that will round to 39.1 grams in a mole. So then, since both those are on the top and I was able to cancel out my moles of potassium, then I'm going to end up with just grams of potassium. So since they're both on the top, I'll multiply. I end up with this value in my calculator. I had, though, originally 1, 2, 3. So I had 3 significant digits in my original number. So I can only have 3 in my answer. So 1, 2, 3. I need to look at this number. That'll cause that to round up. So that will become 130 with a decimal mark grams of potassium. Then if I want to find the mass of, in grams of 15 moles of sulfuric acid, again, sulfuric acid is not one you're supposed to know, but sulfuric acid is H2SO4, just FYI. I gave you some of those in the last unit just because. So first we have to find the GFM of the sulfuric acid, and then we have to convert from moles to grams. So let's find the GFM first. We have hydrogen, we have sulfur, we have oxygen. We have 2 hydrogens, we have 1 sulfur, we have 4 oxygens. We multiply, we look up the atomic masses off the periodic table. So hydrogen is 1.0 grams. We look up sulfur, it is 32.1 grams. And we look up oxygen, which is 16 grams. Then we're going to multiply, so 2 grams, and then 32.1 grams, and then 64.0 grams. Then we take the sum. Again, all of those have one number after the decimal. So my GFM will also have one number after the decimal, and it'll be 98.1 grams per mole. Then we have to convert. So we're going to use that value to convert from moles, which we were given, 15 moles, to grams. We know that for every 1 mole, there's a certain number of grams, which is the GFM. So for 1 mole, there's 98.1 grams. That allows me to cancel out my moles of sulfuric acid, and when I multiply across the top, I get this. Now, I was given this number originally. That has 3 significant digits in it. So 1, 2, 3. I'll look at 4, that's a 1. It doesn't round, so I could write my answer as this. Okay. Then find the number of moles in 11 grams of methane. Okay, so I'm trying to find moles, and I'm starting with grams. So first I need to find the molar mass, or the gram molecular mass of CH4, and then I'll have to convert from grams to moles. All right, so there's C and H, those are the 2 elements, and so I have 1 carbon and 4 hydrogens. So carbon on my periodic table is 12.0 grams. Hydrogen is 1.0 grams. I multiply 12.0 grams and 4.0 grams. Then I add, which will give me 16.0 grams per mole. Now that I know the GFM, or the gram molecular mass, or the molar mass, any of those, I can convert from grams to moles. So I was given my 11 grams of methane. So if grams is on the top, I now need grams on the bottom, and I know that that's equal to a mole. So I know that I have 16 grams for every 1 mole of methane. That allows me to cancel out my grams, and I'm in moles. And since the numbers are on top and bottom, I'm going to divide, and I end up with this number. But originally I only had 3 significant digits. So 1, 2, 3. This is a 5, so that's going to cause this number to round up. So I would have 0.688 moles of methane. It's a lot of stuff to remember. We've got significant digits as well as dimensional analysis plus our new stuff, but we can do all of this. All right. So the last thing we have to talk about for mole conversions is molar volume of a gas. So volume of a gas is usually measured at what we call STP. And STP stands for standard temperature and pressure. And the standard temperature that we use is 0 degrees Celsius. And the standard pressure is 1 atmosphere. And this is kind of foreshadowing some stuff we'll talk about later in the course. But I just want to make sure I give you information as we're going along. Okay? So, molar volume of a gas at STP is always 22.4 liters. That means if I say, what volume, if I have a mole and I say, how much volume is that, then it's 22.4 liters. Okay? So there's 22.4 liters of gas at STP if it has 6.02 times 10 to the 23rd molecules, which remember is a mole. And then there's 22.4 liters of a gas that has a mass that's the GFM of the gas. And remember, the GFM is equal to a mole. All right? So again, we have another conversion factor. So we have 3 sets of conversion factors. We have one for representative particles and the mole. We have one for the gram formula mass and the mole. And now we have one for the volume and the mole. So we have a mole over 22.4 liters, or we have 22.4 liters over a mole. Okay? So let's do an example. What's the volume? So again, I'm looking for liters of this amount of moles of methane. So I start with what I'm given, which is the 0.960 moles. I do my dimensional analysis. If moles is on top, then moles has to be on the bottom. And I want to go to liters, and I know there's 22.4 liters in a mole. So that allows me to cancel out the moles, and I'm in liters, so I multiply across, and I get this number. Well, I only had 3 significant digits to begin with, so I have to go 1, 2, 3. This is a 0, so it'll stay the same. So it's 21.5 liters of methane. At STP, how many moles are there of this much? Oh, nope. I want to know the moles. If I have this many milliliters of gas, milliliters, I need to remember that I got to convert from milliliters to liters. Okay, I can do that because for dimensional analysis, remember that we know if milliliters is on top, milliliters have to be on the bottom, and I want to convert to liters, and I should know that there's 1,000 milliliters in a liter. If you don't remember that, you need to remember that, okay? But we are allowed to cancel out our milliliters then. Now I know that for since the liters is on top, liters has to be on the bottom, and I know that I can relate liters and moles. I know for every 1 mole, there's 22.4 liters. So I'm going to be able to cancel out my liters, and I'll be able to multiply across the top, divide across the bottom, and I'll end up with this number. Well, I only had 3 significant digits in my original number. So 1, 2, 3. This is a 9, so that's going to cause this number to round up. So that'll be 2.42 times 10 to the negative 5th moles of Ne. Okay? All right. So what are all of our conversion factors for this unit? 1 mole is 6.02 times 10 to the 23rd representative particles. 1 mole is equal to the GFM. And 1 mole is equal to 22.4 liters of gas at STP. So this is one way to look at it. I could start with the mole in the middle, and I could be going out or in accordingly, and I would multiply or divide, depending on whether I was leaving from the moles in the middle and going out to one of the various topics that we've talked about, or whether I was coming in, okay? So this is kind of all the information that we just talked about in a nutshell. This is also it. And this actually tells you that, if you're going out, if you go from moles to particles, you're going to multiply. But if you go from particles into moles, you're going to divide. So this one actually tells you, and again it tells you down here, when leaving Moleville, so the meaning you start with moles, you multiply. When you're traveling to Moleville, it says to divide behind that, but I'm not going to move that because then that'll mess up my recording, and I've been doing this too long to stop now. Okay? So again, when you're leaving, multiply. When you're coming from liters to moles, divide. When you're leaving from moles to go to mass, you multiply. When you're coming from mass to moles, you divide. Okay? So that's just one of those things that might be helpful for you as you're going along. All right, so now we could combine all these conversion factors and do more than one. Because remember, we could flip this card upside down, or we could flip this card upside down, or we could flip this card upside down. So I'm going to be given 11.9 times 10 to the 13th molecules. But I want to find moles. Okay, so I'm starting with my molecules. If molecules is on top, then my next conversion factor needs it on the bottom. So I'm going to use this one because that's 6.02 times 10 to the 23rd molecules for 1 mole. That would allow me to cancel out my molecules, and I would end up with 1.977 times 10 to the negative 10th moles. And that has the correct number of significant digits. What would the mass of these molecules be? Okay, well, first of all, I'd have to calculate the GFM as well. O2 is going to be 2 times 16 grams, which is going to give me 32 grams per mole. I had this many moles of O2 from my previous conversion. If moles is on top, then I'm going to now use this one. I'm going to put the moles on the bottom and the GFM on top. That will allow me to cancel out my moles, and I will now be able to multiply across the top and end up in grams. Okay. That should be good. All right. So we did have this 32 that we calculated, so it only had 3 significant digits, so that's why our answer only has 3 significant digits, just for those of y'all checking that. Okay, now I have molecules of isopropyl alcohol. I want to know the molecules, and I'm starting with grams. Okay, so first of all, I'm going to have to find the GFM. I'm just going to tell you that. So C, H, and O. I have 7 carbons, 14 hydrogens, and 2 oxygens. Carbon is 12.0 grams. Hydrogen is 1.0 grams, and oxygen is 16.0 grams. Multiply. 7 times 12 gives me 84.0 grams. 14 times 1 gives me 14.0 grams. And 2 times 16 gives me 32.0 grams. Then I'm going to find the sum of that, which is going to give me 130.0 grams per mole for my isopentyl acetate. So I start with those grams, all right, that I was given, which I gave with I start with 1.0 grams of what I was given. Then I'm going to use those, that GFM, this value, because I'm going to use that conversion factor to cancel out my grams. And I'll put a mole on top. So that cancels my grams out. Then I have moles on top, so I need moles on the bottom. So I'm going to use that because I want to get to molecules. So I'll put the moles on the bottom. I'll put the 6.02 times 10 to the 23rd on the top. That will allow me to cancel out my moles. And I will end up with an answer of 4.63 times 10 to the 21st molecules. So this is just a 2-step dimensional analysis problem is a really way to think about it. All right. So how many sodium ions are in 0.302 moles of sodium sulfite? Okay, we're not actually going to break this down this way. This is a little bit further or above and beyond what we're going to do in our class, so I'm going to skip past this example. So All right, that finishes part one notes. Hopefully this is a good supplement if you weren't in class and or for you to review if you were in class. Okay, have a good one.